Sending.
Slideshow. On the mic. Hello.
Now it is okay, sir.
It's okay?
Okay.
Okay. Thank you, sir. Thank you. So thank you, madam, for the wonderful introduction. Before I start, I would like to congratulate MES College, Department of Chemistry, Principal Dr. Rajesh, and the entire faculty members of the department for organizing such a wonderful program spread over a period of 4 days starting today. Am I audible, sir? Hello?
Yes, sir. Yes, sir.
Okay. So we are all passing through a very, very difficult situation because of the present pandemic. And this type of online training programs have become very popular nowadays. And we are all now subjected to a new normal, and we are all getting accustomed to that new normal. So this is I think I really appreciate the initiative taken by the college for conducting this program or similar programs also, especially for the benefit of student community. So this is one of the best ways of utilizing the time available to all of us. So I hope students will be able to take the benefit of these programs. And without taking too much of time, I will directly go to the topic. So welcome all the students for this program. And we have 4 different interesting topics to be discussed. Now I'm going to be with you all for the next 3 days and discussing about 3 different analytical techniques. Starting with a very, very simple, yet a very powerful analytical technique like UV visible spectrophotometry. And tomorrow I'll be talking about infrared. And the day after tomorrow, I'll be taking about a separation mechanism, gas chromatography coupled with mass spectrometry. So analytical chemistry is all about measuring, all about different types of measurements we are going to carry out on different types of samples. Dr. Yahya has given an elaborate introduction to this. And today we are all, analytical chemistry is the order of the day. Without measurement, nothing happens. In our day-to-day life also, we are doing all this. When you go to a grocery shop, we try to purchase something and we take it, we purchase it either on the basis of weight or on the basis of volume. So there is a measurement involved. You are measuring weight, you are measuring volume, there's a measurement involved. Day-to-day life. So when it comes to these type of analytical techniques, so analytical chemistry is all about different types of analysis that we are going to carry out and different types of sample that we know. So it deals with the different types of separation mechanism, different types of identification mechanism, on different types of samples. And all these different types of analysis can be classified into either a qualitative analysis or a quantitative analysis. And when I hope all the students must have learned all these techniques in their curriculum, because many of the students are at the master's level and a few of them must be in the bachelor's level. So I definitely, I know, because they must have already learned all these techniques in their curriculum, in the syllabus. Now, what we are trying to do, we are only going to talk about the very basic things about these different techniques. I am not going to talk anything very hi-fi. I am going to talk about only the basic things. The idea behind conducting these type of programs are that you should be very, very thorough with the basics. And once you are thorough with the basics, you can always build upon your knowledge. Because I tell the students always when I go for lectures, see, a tall building can be always built. Maybe a 30-story, 40-story, 50-story building can be always built, provided the foundation is very strong. If the foundation is strong, there is a possibility that the building can fall down like a pack of cards. It can fall down. But the foundation should be very strong, and that is the process, the laying the foundation of your knowledge. That is what you are doing when you are in the college or university. Once you are out of the university, once you are out of the college, you are going, either many of you may be going for higher studies and research. Many of you may be getting into corporate world. So you are going to come across different types of analytical techniques for different types of applications. Unless and until your fundamental knowledge is very strong, you'll never be able to effectively and efficiently utilize these techniques. I'm telling you this when you are for a student's life is the most enjoyable part in one's life, because when the students are there, I mean, when they go home, there are people to take care of. The parents are there, sister is there, brother is there. There are people to take care of you. When you come to the university, when you come to the college, there are teachers who will take care of you. But the moment you enter the corporate world, you have to take care of yourself. Please understand that there is nobody to pamper you, nobody to spoon feed you, and you are your own master, and you are accountable for every moment you are going to spend inside the company. At the end of the day, you are answerable. So there is no time for others to sit with you and teach you. So all those learning process, that laying of the foundation, and that is what you have to do when you are in the college or university. So that is the importance of utilizing the time. Time is the most precious part in everyone's life. Time is the most precious thing. Everyone is having equal amount of time. How you utilize it effectively, effective time management is very, very important. So try to learn something. And we are only going to discuss, as I told you before, we are going to only discuss about the basic things, because once you know the basics, you can always read and you can always build upon that. So analytical chemistry utilizes classical wet chemistry methods. I mean, we all know about wet chemistry methods. I am not underestimating the importance of wet chemistry methods. So we are doing a lot of wet chemistry methods, not only in academics, in industry also we are doing a lot of wet chemistry methods. And we also have modern instrumental methods. So instrumental methods will include chromatography when we talk about separation, spectroscopy when we talk about identification, and then there is a third classification which is known as material characterization techniques, where we try to characterize materials on the basis of the physical properties, not chemical properties. There are a set of analytical methods coming under that. Well, now let us come to identification. When I talk about UV spectroscopy or I talk about IR spectroscopy, all spectroscopy techniques are collectively called identification techniques. So in analytical chemistry, we can have three different sections: identification techniques, separation techniques, and material characterization techniques. So identification techniques, there are many different identification techniques available. And I've just shown some very, very important, very popular, most widely used techniques, not only in academics, but in industry. Number one is UV visible spectrophotometry. Very, very simple technique. That's the first member in the family. Then comes the infrared spectrophotometry. We have atomic absorption spectrophotometry. We have inductively coupled plasma atomic emission spectrometry, or inductively coupled plasma coupled with mass spectrometry. It becomes ICP-MS. Then we have fluorescence spectrometry. There are a lot of members in this family. So, but these are some of the widely used ones. So if you look at these different members, then the first one, the simplest technique is always UV visible spectrophotometry. And some of these techniques are very prominent as qualitative techniques, and some of the techniques are very prominent as quantitative techniques. Okay, we will come to that. So spectroscopy techniques can be broadly divided into two types. One is molecular spectroscopy and one is atomic spectroscopy. If you look at atomic spectroscopy, we have two different major members. AS is their atomic absorption spectrophotometry, and then ICP or ICP-MS, ICP-OES or ICP-MS. But these are atomic spectroscopy. These are the members in the atomic spectroscopy division, and they're all basically for elemental determination and elemental quantification. I think Dr. Yahya was touching upon that. Suppose if you have a water sample or any other sample, in that you want to find out very precisely, quantify some of the metallic elements. Then you either go to an AS technique or we can even go to an ICP technique, depending upon what is the expected concentration of those metals in the given sample. Okay. Then the next bifurcation is molecular spectroscopy. There also we have different types, like starting with NMR, we have Raman, we have UV visible, we have 50 AR. These are all members coming under molecular spectroscopy division. So it's a broad classification, molecular spectroscopy and atomic spectroscopy. And I hope you know what is meant by electromagnetic spectrum. Today we are having different types of radiations. Different types of radiance are available. What we see is the sunlight, white light, what we see is a type of radiation. UV light is a type of radiation. IR light is a type of radiation. So we have different types of radiations available today. And each radiation is characterized by two fundamental properties. One is the wavelength range, and the second one is the energy content. So for different radiations, the energy content will be different, the wavelength range will be different. So if we try to arrange all these radiations on a certain sequence, in a certain manner, then we get what is known as electromagnetic spectrum. And what you see on the slide here is a part of electromagnetic spectrum. And different radiations are shown and how they are arranged. If you travel from the left-hand side of the spectrum to the right-hand side of the spectrum, you will see that the wavelength is increasing. So they are arranged in the order of increasing wavelength from left-hand side to right-hand side. So that means on the extreme left-hand side, you will see some radiations which are having extremely low wavelength. And when you go to the extreme right-hand side, you will see some very, very long wavelength radiations like radio waves, microwaves, terahertz radiations, all those. And what is the fundamental property or fundamental relation between wavelength and energy? They have an inverse relation. That means energy and wavelength are inversely proportional. That simply means when the wavelength is more, energy is less, and the wavelength is less, energy is more. That is why you see at the extreme left-hand side, you have all high energy radiations. We have gamma radiations, we have cosmic radiations, we have X radiations. All these are considered as high energy radiations, and their wavelength is going to be extremely low. On the contrary, on the right-hand side, you have radio waves, microwaves. They're all high wavelength radiations, but of extremely low energy content. So that's a relation. So when we talk about UV, when we talk about visible, when we talk about infrared, all these are members in this family. Now, if you critically look, UV is always coming on the left-hand side of visible. That means UV radiation has got higher energy compared to visible radiation. And visible radiation has got more energy compared to infrared radiation because they are coming on the left-hand side. Now, UV, what is the wavelength range? I do not know whether the students are carrying out certain experiments on UV in the laboratory because we have got a well-equipped laboratory in the college. I understand that. I do not know whether they have an opportunity to work on these equipments. But as Dr. Yahya was telling, these laboratories should be, the door should be open to the postgraduate students to enter and at least do some very, very basic experiments so that they get the feel of the equipment. They know how a sample can be analyzed. A very simple experiment can be conducted on this. So they will get to know, and all these equipments have to be very, very carefully handled because they're costly. So there are a lot of do's and don'ts which I will come to towards the end of this discussion. So normally when we talk about UV, I've shown the range as 200 to 400 wavelength. And it is the wavelength is always in terms of nanometer. So 200 nanometer to 400 nanometer is shown as the UV range, the wavelength range of UV radiation. But please understand, for all practical purposes, we record a UV spectrum of a sample from 190 nanometer to 360 nanometer. Okay, that is a normal recording range for a sample, 190 nanometer to 360 nanometer. And visible range, when we talk about visible range, the range is always from 400 nanometer to 800 nanometer. So there is a gap between 360 nanometer and 400, because I told you normal UV range, recording range is from 360 nanometer coming down to 190 nanometer, and visible region is from 400 to 800 nanometer. So what about the gap between 360 nanometer and 400 nanometer? That is known as an overlapping region, because in the case of a UV visible spectrophotometer, which is covering complete UV range as well as visible range, there are two different lights. There are two different light sources. One light source is meant for UV region, and another light source is meant for visible region. So when you're passing from UV region to visible region, there is a changeover of lamp. The UV lamp will be put off automatically, and the visible light will be automatically put on. So there is a region in which this changeover happens, and that is the region between 360 to 400. And that is why it is known as an overlapping region. Okay. Now, wavelength properties of light, I think I can skip also this because all the students have studied this. So light has got wavelength properties. Like if you look at the sea, how the water is coming, water is going up and coming down, it's called a wave motion. So any wave motion, there will be maximum points and minimum point. So a radiation also can propagate through a medium in the form of a wave, in the form of a transverse wave, and there will be maximum points, multiple maximum points, and multiple minimum points. And the distance between two consecutive maximum points or two consecutive minimum points is called one wavelength, or it is called one lambda. And lambda, that is a wavelength, that is the wavelength of that given radiation, and this can vary from radiation to radiation. And you know this very fundamental equation, C is equal to nu lambda, where C is this velocity of light, lambda is the wavelength, and u is the frequency. So wavelength properties of light. Now, when the radiation is propagating through a medium in the form of a transverse wave, it has got certain phenomena such as transmission properties, absorption properties, refraction, reflection. All this can happen. Transmission, the light can get transmitted through a medium. We talk about transmission. The energy can get absorbed by a medium. We talk about absorption. It can get refracted from one medium to another, and also it can get reflected from one surface. So reflection, refraction, absorption, transmission, these are all some of the basic phenomena connected with the wave motion. Now, what you are going to study using a spectroscopy technique? So today you have a UV visible spectrophotometer in your laboratory, and you are getting different types of samples for analysis. Now, what are you going to study? Whether it is a UV spectrophotometry technique or an IR spectrophotometry technique, whatever it is, what is it that you are going to study using a certain spectroscopy technique? That is nothing but when a certain type of radiation is coming and falling on the sample, what type of changes are going to take place in the sample is all what we study by a suitable technique. So that means when the light is going to come and fall on the molecule that is sample, there are different changes that are going to take place. And the changes that are going to take place also will depend upon the energy of the radiation coming and falling on the sample. The radiation can be a high energy radiation or it can be a low energy radiation. And the changes that they are going to induce are also going to be different. So if a low energy radiation is coming and falling on the sample, there are possibly two different types of changes that you can expect. One is known as vibrational changes. We call it as vibrational transitions, or it can be rotational transitions. And if it is a high energy radiation that is coming and falling on the sample, the change is going to be totally different. It is known as an electronic transition. Okay. Now, in the case of UV, UV is a very, very powerful radiation. So it is considered as a very powerful radiation. And because of the high energy content, UV radiation can always induce an electronic transition in the sample. Whereas when we talk about IR tomorrow, IR is considered as a very low energy radiation, and that is going to induce different vibrational transitions in the molecule. And that is a topic of discussion for tomorrow. Now, just a slide I'm showing. Any sample under normal condition has got certain quantum of energy associated with that. We normally call it as the ground level or the ground state energy, and is denoted by E0. Okay. Now, there are upper levels of energy, like from E0, it can go to E1, from E1 can go to E2, different higher levels of energies are also there. And between two different energy levels, there are different vibrational levels and different rotational levels. Okay. Now, any transition from a lower vibrational level to a higher vibrational level is of low energy. And if you consider within two vibrational levels, there are different rotational levels also. And the transition between different rotational levels, they are of very, very low energy content. So these are basically rotational transitions are induced by, or you can say rotational transitions are always studied by microwave spectroscopy, or to a certain extent we can even study by Raman spectroscopy. And vibrational transitions taking place inside a molecule is what we are going to study by IR spectroscopy. And what about UV? UV is a high energy radiation, and high energy radiation is going to induce an electronic transition. So you can see here in the slide, whenever there is a transition from a lower energy state, say E0, to a higher energy state, say E1, and that's an electronic transition, and that is a very, very high energy transition, and that is what is taking place in the case of UV radiation. I mean, you can see from this slide, an electronic transition, you have a sample that is your matter. At the normal conditions, it has got certain quantum of energy associated with the sample. We call it as the ground state energy, that is E0. Now assume that this sample is subjected to UV radiation. UV radiation is coming and falling on this sample. Now, depending upon the type of sample, I mean that's a very important point. Depending upon the type of sample, the sample is going to absorb a certain quantity of energy from the incoming radiation, and thereby the total energy content is going to increase. It has already got E0. That's a quantum of energy associated with the sample at normal conditions. Now it has received additional energy from the incoming radiation. Now the total energy is going to E1. So that is called an excited state. E1 is an excited state. And the difference between these two levels, E1 minus E0, is equal to h nu, or we can write it as delta E. That's the quantum of energy that the sample has absorbed from the incoming radiation. Now, but then why it is called an electronic transition? Because everyone knows about the atomic structure. We have a central nucleus where protons and neutrons are all there, and electrons are all orbiting around the nucleus in various orbitals. So when the sample is subjected to a UV radiation, one electron from the outermost orbital gets energized, and it gets and is getting elevated to a higher energy level. So the one electron from the outermost orbital is pushed to a higher energy level. And since the electron is going from a lower energy to a higher energy level, we are calling it an electronic transition. And for this electronic transition to take place, the incoming radiation has to be very powerful. So UV, being a high energy radiation, can always induce an electronic transition in the sample, whereas IR cannot, because IR has no sufficient quantity of energy to induce an electronic transition. So there's a different type of transition that we are going to study, and that is what we'll discuss tomorrow. Okay. Now a little bit about, I hope you must have learned all this. Absorbing species in UV visible. Electronic transitions involving organic compounds, inorganic compounds, complexes, all these types of samples can take part in this. And a basic process, suppose M is your molecule, and H nu, that is the energy, that is the radiation, that UV radiation is coming and falling on the sample. What will happen, a certain amount of energy will be taken by the sample. The sample is normally, in the beginning, it is at the ground state. And after absorbing a certain quantity of energy, the sample is going to an excited state. M is getting converted to M star. M is the ground state level and M star is the excited level. But this excited level of the molecule has got a very, very short life to the extent of 10 to the power of -8 to -9 seconds. And it will automatically come back to the ground level, giving out the amount of energy that is taken, that is absorbed. It can come out in the form of heat, it can come out in the form of fluorescence, it can come out in the form of phosphorescence. There are various ways, but it can come out. That is one process. And then otherwise, when the sample is absorbing radiation, energy, and it is getting converted into an excited state, M is getting converted to M star. M star, instead of coming back to M, instead of coming back to the ground level, it can get converted into a totally different entity. That is, M star is getting converted into N, a totally different entity. It's nothing but a photochemical reaction. So these are the possibilities when the sample is absorbing energy from the incoming radiation. And you know, there are different electronic transitions and electronic levels. And some of the levels are occupied and some of the levels are unoccupied level. For example, we talk about sigma orbital, we talk about pi orbital, we talk about n orbital, non-bonding orbitals, then pi star orbital, sigma star orbital. So pi star and sigma star orbitals are unoccupied levels, and sigma and pi are normally occupied levels. Now, different types of transitions can go from electrons can get transition from one state, one orbital to another orbital. These are observed electronic transitions. From the molecular orbital diagram, there are several possible electronic transitions that can take place, that can occur. Each of a different relative energy. Every transition is involving a certain quantum of energy. So if we talk about an electron is going from sigma orbital to sigma star orbital, we call it as a sigma star transition, but it is of very, very high energy. Normally, we will not be able to observe those type of transitions in the normal UV visible spectrophotometer available with us. Because the normal spectrophotometer, I do not know whether students know this, the normal UV visible spectrophotometer available in the market today, even that much is the same what you are having in a laboratory, that is from 190 nanometer and it can go to 1100 nanometer. So when I say 190 to 1100 nanometer, this spectrophotometer is covering UV range from starting from 190, and then it is covering visible range. And we know visible range maximum limit is almost approximately around 800 nanometer. But this spectrophotometer is going to 1100 nanometer. That means it is slowly entering the near infrared region. That's called an NIR region. Okay, but you look at the starting wavelength range, that is 190 nanometer. And whatever transitions are taking place below 190 nanometer, your spectrophotometer will not be able to see. But when you consider a sigma star transition, normally these are the type of transitions taking place in alkanes, saturated hydrocarbons, having single bonds. And they all will fall below 190 nanometer, somewhere about 150 or even 160 nanometer. That means it is out of range for our spectrophotometer. We are not able to observe those type of transitions. Very, very high energy transitions. Sigma star transition. Then we have sigma to pi star transitions. Many of the sigma pi star transitions will be able to see. Carbonyl compounds are an example for that. Then most of the unsaturated compounds and aromatic compounds, there will be a pi star transition, which we can conveniently and comfortably observe and measure. Pi star transitions, they're all falling within our measuring range. Then there are N sigma star transitions, where samples containing oxygen, nitrogen, sulfur, or even halogens. And some of the carbonyls also will have a transition from N pi star. So different transitions can take place. Some of the transitions are very, very high energy transitions, like sigma star transitions. For example, I will tell you a very simple example. When we take a measurement in UV, we have to dilute the sample, and we have to make a very dilute sample, and you use your different solvents. And say suppose normal hexane is a good solvent for making solutions many times. So we consider normally in industry also people say normal hexane is UV transparent. UV transparent means it does not absorb UV. But is that statement correct? It is not, because normal hexane is a saturated hydrocarbon alkane. It can absorb UV radiation, but in a region which is not measurable by the equipment. It's a sigma star transition that is taking place around 150 nanometer. Our instrument will not see that because our instrument is starting from 190 nanometer. So for us, for all our practical purposes, we can consider normal hexane as a UV transparent solvent. And we can conveniently use that solvent for making solutions for measurement. Okay, so so you have to, we are coming to a slide where we talk about UV cutoff value also. Okay, so observed electronic transitions, although the UV spectrum extends below 100 nanometer, oxygen in the atmosphere is not transparent below 200 nanometer, it can also interfere. So there are equipments available to study these type of transitions, because when we go below 190 nanometer, there is a region called vacuum UV region. Normal UV spectrophotometers will not cover this region, vacuum UV spectrophotometry, vacuum UV region. But we have equipments which can work in vacuum UV region also. So we can even go to much low below 190 nanometer. But most of the time, what we are interested in finding out transitions that are taking place above 190 nanometer and upwards. Okay, so here it is shown sigma star transitions, saturated hydrocarbons, alkanes, taking place somewhere around 150 nanometer. And some of the sigma pi star transitions, carbonyl compounds, also may fall below 110 nanometer. So not all carbonyl transitions we are able to see. We are able to see carbonyls which are always taking place above 190 nanometer. Okay, so there are carbonyls where N pi star transitions are taking place somewhere around 300 nanometer. Absolutely no problem for us to study those type of transitions. And unsaturated compounds where pi star transitions are taking place, we are very comfortable because they are all taking place above 190 nanometer and under our conditions of the equipment. Now, this I can just skip through. Single sigma electrons are involved in the formation of single bond. What you see on the left hand side of the slide is a sigma orbital, and the right hand side is showing a sigma star orbitals and anti-bonding orbital, non-occupied level. Similarly, pi electrons are involved in double bond formation, and you can see a pi orbital and a high energy anti-bonding pi star orbital. Okay. Now, this I am just skipping because this is already we have discussed about this. Okay. Sigma star, N pi star, and N sigma star, all those type of transitions. So I can skip this. So here I am just showing a slide where divided into different columns. And the first column, it is showing some of the chromophores. And what is a chromophore? I'm going to come in next slide, chromophores. And some of the examples. And what is the type of solvent we can use for making a solution, dilute solution. And what is the lambda max. And what is the type of transition that is taking place, a general slide that I have shown. Now, my question to students is whether every sample can absorb UV. Because you have UV spectrophotometer in your lab, a lot of samples are coming. Whether all these samples can be analyzed by UV? Answer is no. If the sample has to absorb UV radiation, it has to contain at least one chromophore. And what's a chromophore? I am coming to the definition. If unless and until a chromophore is present in your molecule, the sample will be UV transparent. It will not absorb UV radiation. So simple definition of a chromophore: molecules having unsaturated bonds or free non-bonding electrons that can absorb radiation of relatively low energy are called chromophores. Examples include alkenes, alkynes, ketones, aldehydes, phenyl, and some other aromatic species. So they are molecules having unsaturated bonds or free non-bonding electrons that can absorb radiation of relatively low energy. Because if the absorption is at a high energy level, it will go below our recording range. You'll not be able to see that. Okay. So that is why we are specifically saying relatively low energy, and so that it will be falling within the measuring range of the equipment. A chromophore refers to a functional group that absorbs light such as C double bond C, C double bond O, N double bond N, N double bond O, and there can be multiple bondings also. Exhibits a characteristic absorption spectrum in the ultraviolet or visible region. And many times these chromophores can be more than one chromophore can be present in a molecule, then we call it as a multi-chromophoric system. The requirement is at least one chromophore should be there. There can be more than one chromophore, then it becomes a multi-chromophoric system also. We'll see some examples. Then there is something called auxochromes. And what's an auxochrome? It is a functional group that does not absorb UV radiation by itself. It will not absorb by itself, but it will enhance the absorption due to a chromophore. And it will push the lambda max to longer wavelengths, and it will also increase the intensity of absorption. And that is something like a supporter of chromophore. Is that by auxochrome by itself, it will not absorb, but it will enhance the absorption due to chromophore, and the lambda max will always get shifted to a longer wavelength, and the intensity of absorption also will increase. And some of the examples are a hydroxyl group, OH, OR, NH2, thiol, sometimes even halogens also can act like a auxochrome in a molecule. Now, this is a slide showing multi-chromophoric system. Please understand, I'm not going a little fast because otherwise I'll not be able to finish this. If a sample contains more than one chromophore, or I can put it this way, as the number of chromophores is increasing a sample molecule, the lambda max, and I hope all the students know what is the lambda max. Lambda max is the wavelength at which maximum absorption is taking place. A sample may absorb at different wavelengths. When you are scanning from 360 nanometer to 190 nanometer, one X sample may be absorbing at various wavelengths. But at one particular wavelength, this absorption will be maximum. And that wavelength is known as the lambda max. So any quantitative analysis using UV, the analysis should be carried out at lambda max value. Okay. So when the molecule contains multi-chromophoric system, that means when the number of chromophore is increasing in the sample molecule, the lambda max will go to longer and longer and longer wavelength. We can see here is a diolefin, unconjugated diolefin, where the lambda max is somewhere around 185 to 190 nanometer. And when we talk about a conjugated triolefin, the lambda max is already shifted to 250 nanometer. Say from 190 nanometer, it has gone much longer. It has gone to 250 nanometer because it contains 3 chromophores. Instead of 2 chromophores, it is containing 3 chromophores because each double bond is a chromophore for us. Okay, diolefin, triolefin, 2 double bond system, 3 double bond system. The number of chromophore is increasing. In some of the polyaromatic hydrocarbons, polynuclear aromatic hydrocarbons, we'll see the lambda max is getting shifted towards longer and longer wavelength because the number of chromophores is increasing in the molecule. We will see an example also for that. Now there is something like solvent cutoff, and this is an important slide because, as I told you, in the case of UV, we are making a very dilute solution, and because UV, the concentrational solution is very, very important. And we can use different types of solvents. I have shown certain solvents here like acetonitrile, chloroform, methanol, isooctane, even pure water. And every solvent has got a different value. I mean, that is called a cutoff value. Acetone 190 nanometer. Chloroform is 240 nanometer. What does this mean? When I take, suppose, for example, if I take chloroform, it has got a cutoff value 240 nanometer. That means below 240 nanometer, the chloroform absorption will increase. And above 240 nanometer, chloroform absorption will decrease. So while choosing a solvent for making a solution for a measurement in UV spectrophotometry, you have to know what is the solvent cutoff of the solvent. Many times you can get this value from the literature, or many times when you're buying the solvent from a reputed manufacturer, they will also give you a certain certificate of analysis where they must be mentioning what is the cutoff value. And if you don't choose the right type of solvent for making the solution, your absorbance measurement will not be proper. Please keep this in mind. This is an important slide while selecting the solvent, either for UV spectrophotometry or even for those people who are using HPLC analysis, we're using a UV visible detector system. So this is a very, very important also solvent cutoff value. You have to be very careful. This is an example of a dye sample. It's a water-soluble dye. And different, if you look at the structure, there are 6 different benzene rings in this. And each benzene ring is a wonderful chromophore for us because it is a conjugated it's a conjugated system. It's a 6-membered ring structure having conjugation. And it is a wonderful UV absorbing chromophore. And in this molecule, similarly, we have 6 different benzene rings. So there are multiple chromophores present in the sample. And because of this, you can expect the lambda max at a very, very long wavelength. It may sometimes even go to visible region, crossing 360 nanometer and entering the visible region. Say from 400 onwards, it is visible region for us. So it may be having a lambda max in the visible region, and then we can do a colorimetric analysis. That means color intensity measurement. Instead of a UV analysis, we'll be doing a colorimetric analysis. I mean, looking at the structure of a sample, you can decide whether the sample will be having UV absorption or not. Tryptophan is an amino acid. It contains a benzene ring. Naturally, you can expect the UV absorption for this. Another wonderful example is vitamin A. An oil-soluble vitamin A, normally analyzed by HPLC with a UV detector. And look at the conjugation, and it is an excellent UV absorbing material because of a very high degree of conjugation in the molecule. So it's a multi-chromophoric system and has got very high UV absorption. And look at the spectrum of anthracene. It's a member of the polyaromatic hydrocarbon. So it's again an example of a multi-chromophoric system. And if you look at